All right, so how to find the details, how to find where the association is stronger and when the association is less strong. When I say where, I mean for which categories, for which combination of the categories. We will still use the residuals, but in this case, we will use what is called standardized residuals. So the idea is following. When you make a test for association, you analyze residuals, right? So this is the residuals. So it's a difference between observed and expected frequencies. To make the test, you take a sum of squared scaled residuals, and that's we know that it follows the chi-square distribution. However, if all requirements are met, you can take only this difference without squaring it and divide to this one. And that will give you the standardized residuals, because that's exactly the standard error of the residuals. Okay. So what you see here, it's a z-score. It's a z-score. So this residual, the standardized residual, it's simply a z-score for residual. But look, can you see this RC? What means RC? It means a particular combination, a particular row and particular column. So it means that you can compute standardized residual for every combination of the categories. And it means that you can assess how big this residual is for every combination and find out for which combinations this association is stronger, for which combinations this association is less strong. And since it's z-scores, we know that the average of z-score is 0, the standard deviation of z-score is 1, and it means, and you know that 95.5%, for example, right, of z-scores will be located between 0 plus minus 2. So it means that if z-score goes beyond plus minus 2, it means that the z-score is extreme. So it means that this particular residual is very likely not observed just by chance. It's very likely you have some systematic association here. So again, let me show you an example. So these are the observed frequencies, the expected frequencies, and the difference between observed frequencies we calculated. For example, if you see this RC, it means one particular row and one particular column. For example, to calculate D11, we need to take this one, right? First row, first column, and that will be only the difference. We still need to normalize it. How to standardize it, not normalize, but standardize. You remember, this is the E, it's this expected frequency here. And R, it's how many values you have in this particular row. So in our case, it's 71, right? And C, it's how many values you have in this particular column. In our case, it's 16. And N, it's a total number of values, 141, right? So let's do the calculations. So I take, for example, Coke and McDonald's in this case. You can see that it's this column and this row. So 7.25, it's the difference between the observed frequency and the expected frequency. And then this is the expected frequency, right? So this is 71 and 71 because it's 71 number. It's how many observations I have in this row and also how many observations I have in this column. Just by chance, I got the same value. And then you can see this is N and this is N. So if I do this computation, I will get 2.44. And then you can see already it's way beyond this minus plus 2. So it's pretty extreme in this particular case. Okay. And then if I just go on and compute all these standardized residuals, this is the table I get. And then you can see, for example, here, z-score is almost 0. So it means that for this particular case, for BK, we don't see any association. We don't see that, for example, people who go to BK, they prefer Coke or Pepsi. We don't see it. We don't have evidence for that. If you think about people who prefer McDonald's, you can see that here you have a positive z-score. So it means that the number of observed frequencies is larger than the number of expected frequencies, right? By 2.44 standard errors. Here you have negative z-score. So it means that number of observed frequencies is larger or smaller in this case than number of expected frequencies, also by 2.44 standard errors. So it means that here we have more than we expect and here we have less than we expect, meaning people who go to McDonald's or who prefer McDonald's, they tend to drink more Coke than Pepsi. And then in this situation, we have other way around, right? So here we have by 2.49 standard errors larger than expected. So the observed frequency, this one, by 2.49 standard error larger than this one. And this means that the observed frequency, this one, is by 249 standard error smaller than this one. Again, if you think about normal distribution, it's way beyond this 95.5%, right, cases. So you can even compute the real p-value kind of for this. But if you just use this plus minus 2 rule, it also will be a quite rough but pretty good estimation. So again, it means that people who go to Sunset Boulevard, they prefer Pepsi over Coke. So now you can also see all the details. Okay. And actually, you don't need to calculate the standardized residuals by hand. You can also use this chi-square function, which makes the test for association. And then if you write $stdres, standardized residuals, don't mix with normal residuals because it also shows you the normal residuals, not standardized. You remember that m, it's a variable that we saved the results of the test, the outcomes of the test into. Then you can see that this is exactly what we also have here. You can see the values are they're actually identical, right, if you round them. Okay. So that's actually it. And it means that we can correct our conclusions that we made before. So this conclusion is not valid anymore, does not provide details. We can get rid of this conclusion and then write additional point here, use standardized residuals to get the details. Okay. So that also, this video concludes the whole learning sequence. So now you know also how to visualize, how to summarize information about qualitative variables, how to make an inference, and also how to assess association between any two qualitative variables. If you need to assess association between 3 or more qualitative variables, you can use what is called Poisson regression, and there are other methods, but these are a little bit beyond the scope of our course, so you can learn later if you have a need for that. Okay. So that's it, and then the next learning sequence will be devoted to non-parametric methods.